such our next talk's guests from the Apache Hudi community. I am very excited to have them today because you don't see some of them giving talks often. So Vinoth Chandar is the original creator and a VP of the Apache Hudi project. He also has a keen interest in unified data storage processing architectures. He drove various efforts around stream processing, Kafka at Confluent, and in the past, Vinoth has built large-scale mission-critical infrastructure systems at companies such as Uber and LinkedIn. Raymond Xu is also another PMC member from the Apache Hudi community who leads the data lake team at Zendesk. And take it away, Vinoth and Raymond.
Hello. Yes. Okay. All right. I hope the audio's working.
Yep.
All right. Cool. I'm trying to find the screen share here. Okay. It shows up now. Yeah, let's see if you can see the screen. Okay, you can see the slides. All right, cool. Let's get started. It's a pleasure to be here, and I know we're starting with a pretty dramatic title here, path forward and all of that. But in over the next 25 minutes or so, what we're going to talk about is we first going to talk about. We recently did a community-driven sort of re-positioning and redescription of the project. It's changed a lot since it started, and we're going to discuss the platform components, and then and pick out two important areas from that, which we are investing in and thinking about and collaborating on. So we'll generally talk about the problems there and strawman approaches, while then we'll also give you some pointers on how to engage, and hopefully we can. This community, I think this should be like a very relevant talk. All right, and let's get started. So yeah, just a little bit of an intro, very brief. I'll be like just zipping through these things. If you want a bigger expanded version of that, I encourage you guys to look at the ApacheCon talk that we did recently. It's available on the YouTube Apache Software Foundation channel. Again, the two areas that we're going to discuss. The first one is table metadata. We discuss like how we manage table metadata today and what are some of the surrounding context and problems around it, how we are thinking about solving them and taking kind of like generally the data lake ecosystem forward in terms of query performance and scalable metadata management. And maybe one of the most favorite topics here is caching. How are we thinking about caching? Because a lot of caching work has already been done even before Hudi created or as Hudi grew. But Hudi has really brought mutability transactions and a whole bunch of other things on the storage side. So how do we now make them work really well? We'll share some ideas around that. And then, we'll leave you with some thoughts on the community. So high level, this is how we see most of our users use Hudi. They either, have some of the data sources. We have built-in tools called the Delta Streamer tool to CDC data in our event logs and manage them, make a fully managed tools, ingest tools in Flink and Spark. You build a set of raw tables, and then you're able to query them with all these engines for either your, regular data lake analytics or write more batch ETL pipelines. Then Hudi also exposes a lot of the underlying change logs to some of these tables. So you're able to also build more incremental ETL pipelines using Hudi's libraries, right? And this creates an ecosystem where Hudi has a lot of capabilities to manage data. And then, so we are able to actually make, have a good separation between your very optimized data plane and all of these query engines that sit on top. And going back a little bit down memory lane, Hudi was the original system that pioneered the current serverless transaction layer that you see over lakes, right? We started this project way back in 2016, and started as a multi-engine and decouple completely storage from all the different engines. We introduced notions of copy on write or merge on read, different ways of essentially organizing data for either column or query performance or ingest speed. And we can see, like we brought change capture on data lakes, and we can see that some of these ideas are pretty broadly borrowed in other places as well, right? And to quickly give you an overview, right? This is all the different layers in our kind of like stack. We built all of this on cheap, scalable, Hadoop compatible storage. It can also work on in-memory file systems like, let's say, Alluxio. And it's completely built on open file formats and data formats. And at the lowest level, what we provide is actually a transactional database kernel. This is essentially what the project started with. And this has what we call what's now termed as like a table format, right? Essentially like something that stores file layouts and schemas and whatnot. And then we build a bunch of indexing schemes for faster updates, deletes. We also have a set of these daemons that you will find in most databases, right? Which are doing file sizing, cleaning, compaction, and all these like other database kind of like background tasks. And then we provide different concurrency control mechanisms around that. And on top of that, we have SQL and programmatic access to read and write data. We have keys, updates, deletes, as you may know, time travel queries, and change capture or incremental queries, as we call them. And right on the top, there is easily you can get write and read access from your most favorite query engines. And we've also built, or I should say, like as a community, we've got a lot of contributions and done a lot of awesome work around a higher set of platform services, which encapsulate, data ingestion or incremental ETL or commit notifications, these deduplication. These kind of things are often things people run into when they're building their data lake. We've also sort of like built out a rich set of like tools around that. So the remainder of it, I'm going to the main point is it's a complete kind of like platform. It has like a lot of platform components. We try to make all these things, work well together. It supports kind of different programming models, and it's yet optimized for data lake workloads. And yeah, it's the main thing that we focus on is we try to integrate these components really well, because in open source often there's like a lot of different things solving the same thing, but sometimes the loose coupling means you need to integrate a whole bunch, right? We try to, at least within our context, try to make a good job around that for users. So we can read more about this entire thing there. I'll simply gloss over these, which is we have a table format, which is based on, we bucket files into file slices and groups, and we publish kind of like all our activity to what we call like a timeline, and then it gets replicated into another internal metadata table, which stores more information, right? We'll revisit this later. And an individual file slice itself, we have a base file, and we log any deltas updates against those base files. This way, we're not rewriting entire Parquet files every time, like let's say a single record changes, right? And then we can embed any base, open file format in some of these base and log files. And like I mentioned, we have like a bunch of indexes today, an external index or join based index, Bloom filter based indexes to kind of speed up upsert deletes for different scenarios. You can go to Hudi and search for like an index. You'll have a blog post which explains different workloads and walks you through that, right? And concurrency control, this is I think worth maybe spending a few more seconds here. So the thing is, Hudi makes a very conscious effort in distinguishing between writers and internal processes to Hudi. So all the internal processes within Hudi don't block each other at all, because they are actually aware of each other, what we call as MVCC or multi-version concurrency control. And the writers themselves do have like locking and more traditional lock-based optimistic concurrency control. And we are kind of like, laying the groundwork to have fully lock-free kind of transactional things using CRDTs by end of the year. And I'll skip like writers. We do like incremental and batch and all of these operations you'll find. We support record level merges. You can actually write a custom merge if you want, something that you can find that TikTok and ByteDance and like users leverage at large scale when they're doing CDC ingestion or even incremental pipelines, right? And readers, we support like a bunch of engines, and again our specialty being the fact that we can push incremental change streams right into the storage, so we can be like really efficient at reading these things up, right? And I'm going to like quickly go through this, but let's talk about table metadata, right? So table metadata, what qualifies? What do we really mean by table metadata? So it can be, the schema of a table, column names, types, keys, partitioning, and when you're changing the schema, you're also like storing different versions of the schema. They're typically small. You can store most of it within 1 MB per version, right? And then you have files and objects that make up that table. So you have length, paths, URA schemes, and something like 2 million objects. You need tens of megabytes to store these things. It's not like very small, but it's like it's workable, right? But stats, if you look at it, you can collect min, max, nulls per column, per file, and for 2 million objects, you're going to need like some hundreds of MBs, right? Because there is a multiplicative factor here that the more columns you have, the more metadata that you have. The faster you write, the more files you generate. So there is like a balance to strike here. It's not very, very small cost to ignore in terms of IO. So redo logs, essentially, these are all changes to the metadata, like, new files being added, like new transactions being committed, optimizations and everything else. So if you keep committing 200 KB, metadata every minute for a year, this history, and you want to like, maintain like a history, go back in time, do point in time lookups, query like any different snapshot of the table. So you need to like index and kind of like manage around 100 GB of data. It's not like something that you can easily ignore or store in like a single file on here S3 or something. And like I think there's a lot of confusion on like indexes and stats, right? Databases and also Hudi treats them very separately. Indexes are something where you map like something that's an order of a record, right? Something like a secondary field to something else, right? It can be like much larger actually, as you can imagine, than any of this metadata. So that's not what we're talking about. Hudi will have different indexing schemes, and that's probably like for another day. So how is it stored in Hudi today? We store the schema together with our redo log, which we call our timeline, and it's in a folder called .hudi under every Hudi dataset. And this gets synced out to different meta stores post commit. So the source of truth is always our redo log. Files and objects, so there's an internal metadata table and there's like a partition. So it's another Hudi table within a Hudi table. It has another partition called files, so you can read file listings from out of that. Or sometimes we just list storage, right? For example, at Uber or like large scale HDFS deployments, or maybe the same case for something like Alluxio as well, right? Sometimes if you have it in memory as server, it's going to be like much faster than you reading like 10 MB out of storage every time. So we support all these different methods instead of forcing people to use a same thing every time. Redo logs, this is an event log, like I mentioned in the .hudi folder. We keep a constant amount of the log, like essentially, the active transactions stay there and then everything else gets archived out. We are thinking about doing a better job at, organizing that archived information. For now, it just gets archived out. So statistics, we don't, right? That the reason is, again, why I mentioned, it's actually a large amount of data for the kind of use cases, like, if you want to do like real updates, fast updates, or even like, minute level sort of thing that I talked about. So we fetch it out of file footers now. Again, like if you're parallelizing it like what Spark does, engines do, actually sometimes it can be faster than reading it out of a file, right? But now we are actually investing a lot into this. So a lot of work has happened where people have stored these like statistics, especially around in like, JSON or Avro files, right? And then the problem with that is scaling that for really high scale writing. If you have 1 terabyte of data, you want to like write very quickly 16 MB files, something like that, 100 columns, you end up with having to store 6.5 million entries in like a single Avro or JSON file, right? And then as you can see in the benchmark, you can take anywhere up to 26 to like 30 seconds with Avro or even Parquet for that matter, let alone JSON, to read this out, right? And then you'll be reading 100 MB, 200 MB every read. This is like a lot of time for you to plan anything, right? This is single table, correct? So this is pretty slow. So we are doing this RFC 27 effort that currently, essentially it should be titled Flat Files Are Not Cool, but it's about data skipping. We are building it in a way that it's more indexed with interval trees and smart data structures that can skip, and we can bring this down to something like 1 second-ish thing, right? But the main point of where I'm getting to is it's still not enough, right? If you have 30 table or 20 table join, each planning like this thing takes like 2 seconds, then you're not going to ever finish planning in a minute. I know from where we were, the formats now feel like rocket science, right? Oh, I can store all the stats in a single file, but it is not where, let's say, cloud warehouses are, for example, right? So Hudi has always had a meta server. It actually runs in the driver embedded, and it kind of like caches file listings across executors, softens the load on the S3, prevents you from throttling issues and so forth. And then even on our own internal metadata table, right? We don't end up reading 10 MB every time. We cache it in the driver and then serve it out. This lets us build like a multi-level kind of like caching, more performant way of managing metadata. So we are trying to kind of invest into extending that out as a clustered service, adding new locking APIs, bring in all the stats and the redo log and everything into that. And then, yeah, you can easily shard it by table DB and have it working in some of our favorite cluster managers, right? So this is, and then there'll be options to back it with like a local RocksDB instance like it is today, with recovery from the cloud storage, or we can, also push it into some of the newer transactional stores like Spanner or Foundation or like what have you. Right. So this is a basic idea with that. I know I'm a little bit over, so Raymond.
All right, thanks, Vinoth. So I will cover quickly on some ideas around caching, like building a caching layer on top of Hudi tables. Next slide. Yeah, so the idea comes from a problem with today we have more and more commits coming in. We tend to do to achieve faster, smaller latency. This results into a lot of small objects on the cloud storage, for example. It's going to cost a lot of on I/O from both read and write side. And the file system level caching is not enough. It's usually not fast enough to meet the requirement. So the idea is we want to build a real caching layer on top of Hudi tables. And Hudi's file group concept fits nicely into this caching paradigm. So on the right side, you see the Hudi file group is actually consists of a base file, which is usually Parquet, and the log files, which comes in as a row-based file format. So the base file and the log file together, they become a file group. So why I say it fits into the caching pattern is the file group is the smallest unit to be compacted. When I say compacted, means the log file is going to merge with the base file and create a new base file. So that's how the data is being updated throughout the time. So with this unit to be compacted, you can also control the size of the file group by configure some properties. So this will make it a proper size for storing the cache store. Also, the compacted data serves the purpose of having a real-time view on top of the Hudi tables. This will save computation when you're doing real-time query on top of Hudi. Next. So we have some design consideration when we want to build this cache layer. So the first scenario is it's typical change data captures flow. We have coming data from the top and it writes to log files. And this fits nicely into the refresh ahead cache pattern. So when Hudi ingests CDC data, in order to make them available for query, we typically want to run compaction. And in this caching scenario, we do something called a micro compact. It's just compacting on the level of file group and saving the cache. So that's a pre-computed result for people to fetch. On the other side, we have a read-through cache. This is catered for usage. We can build a cache layer to help fetch the data and make it available for more frequent queries. And people can set LRU or LFU for TTL strategy based on different scenarios you may want to choose. You may want to set both for different prefixes. For example, if you want to TTL, you may want to set different TTL strategy based on the partition column. So next. Okay, file group also fit nicely into distributed caching because file group can be identified by a unique ID. You can consistent hashing this ID and make the same file group always updated on the same cache server. And we can also have we should also have a coordinator node to help identifying the server to set the cache. So the timeline server we not just talk about can be a good candidate for this purpose. The next is about transactionality. Hudi has transaction support from support from the beginning. So we want to make sure that only the committed files can be cached. And also when we do rollback during the transaction, we want to make sure the cache is also invalidated. Lastly, we want to make sure the caching layer can be pluggable. So by defining some APIs for the cache to interact with Hudi file groups and also support other common caching APIs, we should be able to make the caching layer easily swapped with different implementation. So from the right side, you can see an example. Alluxio could be a potential good caching implementation here. Okay, that's a quick walkthrough of the cache. So lastly, I want to also touch on the community overview. So we could never come this far without support from the community and the collaboration of different organizations and contributors. So to show some numbers, we have very diverse community. We have 1,200 users on Slack. We have more than 200 people contributing on GitHub. We absorbed more than 20 PMC members and committers from more than 10 organizations. We also have a very well-established process for proposing new features in terms of RFC. So it's basically a design document to illustrate big new ideas, and people can come in and comment and finalize it. So people tend to discuss over the email list, and then they will file JIRAs to follow up the implementation. We also have a very so in terms of user support, we have a very good also on-call rotation for handling the user issues on GitHub, and also we triage them and filing tickets accordingly. So yeah, so just to highlight some big ongoing work in terms of these RFCs, we're supporting Z-order range indexing to improve performance. We have usability support to support Kafka Connect and Google BigQuery. Also, we want to make a full schema evolution working with Hudi. And also there are other major things like supporting error tables and supporting Presto. It's all about making things more easily to use within Hudi's platform. So lastly, we have we're also very broad adoption across the industry. You can click the link and see the Power BI page in Hudi website. You can see from other companies' usage there. So please engage with us through all these links and channels. So yeah, that's all from for this. So thanks. So any questions?
Thank you very much for the talk today. I'm glad to have you guys. So I have here actually Adit Madan will be the moderator for this session. You guys have met with Adit Madan, who is our product and program marketing manager. Adit, take it away.
Hi, Vinoth. Hi, Raymond. Thanks for the talk. I learned a great deal from it. I have a couple of questions. One of them, which just poured in on Slack. There's a user who's talking about the maturity of Hudi. So he starts off with, first of all, congratulating you on the great information that you provided. And then he's asking how mature is Hudi DBMS compared to other RDMS in your view as of today? And specifically, he's interested in the perspective of ease of adoption.
So I can try to take that one. So when we say DBMS, honestly, like I can probably speak for the category as well. I don't think we Hudi is close to as complete as like any DBMS or even this entire category of even other table formats and other things that are in the mix, right? This is actually one of the reasons why we didn't like stress on like transactions a lot early on, because like when you say transactions, people come to expect like kind of the transactional performance of databases, right? Which is not what some of these things are built for, right? So in terms, so Hudi provides like a single table, multi-writer sort of like abstraction, like transactionality for you with change logs, but we doesn't have any of the advanced features like foreign key joins or like the more the complete set of like indexing mechanisms or any of these things. Hudi does have good set of like operational tooling around like the storage optimization pieces, the data management angle, and all of those things. For you to get started, yeah, we actually, for example, if you have a Kafka cluster or like a data lying on S3, you can just get started by issuing a Spark submit command, start building your Hudi tables. And then thanks to, again, the broader community support, we can be queried from most engines, right? Presto, like Spark, what have you, across different vendors. It gives you all that optionality to, deploy a cache, not deploy a cache. And so that's the lens to view Hudi at. If you try to do, let's say, 10 transactions per second or something on Hudi, it's not going to work. Right? It's not really the transactional store in the same breadth as RDBMSs.
Understood. Thanks, Vinoth. I have one more question. Vinoth, I know you began the talk by introducing Hudi as a serverless platform, and then during the talk, you talked about the timeline server and the need that's something that you've already had and building out like a dedicated server. Has there been a change in philosophy with respect to the use of servers?
So two things, right? One is Hudi. So there's a data plane and then the control/metadata plane, right? So if you look at traditional database architectures or even like warehousing architectures, they use like you don't write through Snowflake directly on S3, right? You go through a Snowflake cluster, right? So that's the data plane. So that will remain serverless, and that is what we originally did was we showed how you can build like this database semantics, at least like some version, like the kernel of it, without having any long running servers, right? But looking back, and this has been something, I come from a database world. If I unwind the stack, SQL DB, Voldemort, Oracle database server. So I mean, there is merit to having a meta server and a meta store. We actually thought a lot of these metadata control plane problems would go away with the new Hive server implementation probably by now, right? But since that hasn't happened, and we are actually starting to, that's where we are now, right? We are hitting these metadata limits to plan queries. So we are kind of like extending out, like in like pulling our internal component that we had to cache metadata and everything, making it more full blown. So Hudi will still have data plane be fully serverless, right? That is how you can now scale to thousands of nodes writing directly on S3. We don't want a server layer to stand between your writers and S3, but metadata should be like more indexed and more managed. The world is not where it is 5 years ago, right? We didn't have any transactional, hosted, managed, SQL stores, scale out data stores back then. Now we have Spanner or like a Cosmos DB. Every major cloud provider offers a managed data store. I think we should take advantage of that and build like a metadata service, which is more modern and can actually bridge the gap between like cloud warehousing and data lakes. That's kind of like, just hopefully that puts it into perspective.
Yep, it does. Thanks for that answer. One last question, Raymond. I know you went into some detail about caching with a dedicated cluster and the embedded approach. Can you maybe elaborate a little bit about the trade-offs in your mind as like caching embedded in a process like Trino or Presto versus the dedicated servers that you were talking about?
The dedicated server, I think that's we need to make use of those to make sure it needs to support some file group compaction that we have specifically for Hudi. So this is like the first important scenario that needs to be implemented. So I'm not sure if any of the embedded caching would need to support that. But as I said, the pluggable API should be able to allow the other caching layer to just plug in and then do the same operation. So this is basically an idea that we have. It can be easily extended to other to make other caching technologies to support it. Does that give you an idea about it?
Yeah.
Cool.
I think that's all the questions we have. Thanks again for presenting.
All right, thanks.
Thanks for having us.
All right.